The extreme value theorem, which you are allowed to call the capital E, capital V, capital T. F of x has at least one absolute maximum and one absolute minimum on a closed interval. This is extremely important. This is closed. There are endpoints. As long as f of x is continuous on that closed interval. Every continuous function that has a starting and ending point must have at least one absolute maximum, one absolute minimum. The logical question that you might have is, how do you know which of the points on that graph are candidates for being the highest or lowest? Well, lucky for you, we have the candidates test. This tells us where the extrema are going to occur. The only locations an extreme value may occur is at a critical value of the first derivative or at endpoints on the closed interval. So how do you use the candidates test? 1, find all critical values from the first derivative only. Second derivative is not of importance in this context. 2, make a table and list in that table all the critical points, that's x and y values, and endpoints, those are x and y values. Then look at the y values, whichever one's the biggest, that's going to be the absolute maximum. Whichever one's the smallest is going to be the absolute minimum. Let's look at an example. Use the extreme value theorem to locate the absolute extrema of the function of f of x on the closed intervals. So let's check this out. I'm just going to copy this so I can see it well. So according to the candidates test, the only candidates we have to worry about are the endpoints of this graph and any critical values of the first derivative. So let's find some critical values. To do that, we're going to take the first derivative and we're going to figure out where the first derivative is equal to 0 or it's undefined. Just use the power rule there 3 times. I could factor a 3 out of this, and then this is going to factor into 2 binomials, an x plus 3 and an x plus 1. So f prime of x could be equal to 0, and f prime of x could be undefined. In this particular problem, it's never going to be undefined because we don't have any denominator. You know, a logical question I should have asked at the beginning, can we use the extreme value test on this? And the answer is yes. We're looking at a closed interval, equal signs here at the end, and this function is continuous. So what would make these equal to 0? Well, we would have x plus 3 equal to 0, and we would have x plus 1 equal to 0. So we would get x equals negative 3 and x is 1. So we found critical values of negative 3 and 1. Those are 2 of the candidates. Another candidate that we can find is from the endpoints of this interval. So if we look back just real quick, how do we use the candidates test? Find all critical values from the first derivative. Just did that. List the critical points and endpoints in a table. That's what we're going to do next. I'm going to make a little xy table. And my y table is going to be, you know, this whole mess here, also known as f. So my endpoint at negative 4, and then I have a critical point at negative 3, then I have a critical point at 1, which is also an endpoint. So I just need to figure out what's the y value going to be for each of these. Whichever y value is the biggest, that's going to be my absolute maximum. Whichever one's the smallest, that's going to be my absolute minimum. Unfortunately, this is going to be a little bit of work to put this in. Let's just assume that this is a calculator problem. I don't think they would ever have you calculate something this complicated without a calculator. It doesn't seem AP-like. So using a calculator, when I put -4 in, I got 6. When I put -3 in, I got 2. I made a mistake here. I'm so sorry. This is, first of all, 1 is not in the domain. This was supposed to be a -1. X plus 1 here, set equal to 0. I'm going to get x is -1, not +1. So my apologies. If I put a -1 in, then I'm going to get +6. So this is real easy at this point. This one and this one has to be the max because that's the biggest y value. This one here has to be the min. It's the smallest y value. So to answer the question, the absolute maximum, the direction said to locate the absolute extrema. Technically, to locate them are x values. But a lot of people have trouble with determining if they're supposed to find the x values or y values. So I'm just going to list the ordered pair, -1, 6, and -4, 6 is the absolute maximums, as the points that make the absolute maximums, and the absolute minimum is at -3, 2. Technically speaking, when it says locate, those are x values. Those are locations. Let's check out. We can use the same work over here for this because it's the same function. This interval is from -4 to 1. So we don't need to repeat any of the work that we just did. Don't rewrite the work. I'm just making reference to it here. I'm going to make a table of values. I got x and f of x. We have the candidates that we choose for this are the n values of -4 and 1, and the critical values, which are -3 and -1. If I were to put this into a calculator, trying to make a table nice here. If I put this into my calculator, I would find that if I put a -4 in, I would get a +6. We already knew that. If I put a -3 in, we would get a 2. We already knew that. If I put a -1 in, we would get a 6. We already knew that. The only one that's new is this 1. If I put a 1 in, I would get a -14. So here's what that tells me. I'm running out of real estate here. This is their absolute minimum. These two are tied for the maximum. So we have the same absolute maximums, plural, that we had last time. We have a new absolute minimum that's at 1, -14. So that is how you use the extreme value theorem. Now, the one thing you got to be careful about is making sure that you're using it when you can use it. So let's check out these three fellows here. For each of the following functions, state specifically why the extreme value theorem is or is not applicable on the interval from -5 to 0. Well, if you look at this first one, hopefully you remember from pre-calculus, this is going to have a excluded value at -3. This function's not defined at -3 because the denominator is equal to x plus 3. -3 is in this domain. that means this function is not continuous. In order for the extreme value to happen, you have to have a continuous function. So we could say x cannot equal -3. Therefore, h of x is not continuous on its domain. It's important to say on its domain. And that's important to say because if this ended up being like a -7, that's not in the domain, well, we don't care. We only care if it's continuous on the domain. Since h is not continuous on its domain, the extreme value theorem does not apply. How about number 2? Well, what's the domain of this? If you remember from pre-calculus, an even root has to be equal to or greater than 0. So if x minus 3 has to be greater than or equal to 0, that means x has to be greater than or equal to 3. Well, if you look, it's saying this graph only exists when x is 3 or bigger. This domain is to the left of that. So the extreme value theorem does not apply to this as well. So we could say g of x is only defined on the domain 3 to infinity, and 3 is inclusive. Therefore, g of x is not continuous on -5 to 0. Therefore, the extreme value theorem does not exist. Last one, number 3, natural log of x plus 7. Now, hopefully you remember also from pre-calculus that our argument, the argument is whatever is to the right of the logarithm. The argument has to be bigger than 0, which means x has to be bigger than -7. Well, the domain we're looking at is from -5 to 0, which is bigger than -7. So we could say function f of x is continuous on the domain -5 to 0. Therefore, the extreme value theorem applies. Cool. That's the end of that video. We will do another where we do some more examples of this.